Hello, today we're going to be talking about Earth's atmosphere, which really is the beginning of our study of meteorology. The end of Unit 5 and all of Unit 6 is all about weather and climate, which kind of fall under meteorology, which impacts every aspect of your life. And did you know that the US has the greatest variety of weather across the entire world? It can be thunderstorm here and a hurricane in South Carolina and a blizzard in Colorado and bright and sunny in Nebraska and a volcanic eruption in Hawaii all at the same time. The US has the most variety. Meteorology is going to cover everything from temperature to moisture and humidity to the heat on Earth and wind and rain and how pressure affects things, the seasons, the air quality. There's pollen right now, which then allergies have been bad, drought and severe weather. All of this is kind of wrapped up in meteorology. And we're going to break it into two distinct things, weather versus climate. Hopefully this is familiar, but weather is the short term, constantly changing, what is happening right now in a small local area, what's happening in my neighborhood, on my street, in my county. There have been times where one side of the parking lot at Target is getting rained on and the other side is not. And then an hour later, there is no rain anywhere. That is weather. Climate is the long term, over decades and centuries, and it is the accumulation of kind of generalized patterns. What happens in the Southwest United States over 500 years? That is climate. And it's kind of all of your different things stacked on top of each other. That the Southwest United States tends to have a drier, hotter climate. Or that in Alaska or near the North Pole, you tend to have colder, drier climates over long periods of time. This is not what's happening tomorrow. So, the first part of studying and understanding weather and climate or meteorology in general is going to be knowing about the atmosphere. The atmosphere, you probably, hopefully know, is kind of the envelope of gas that surrounds our planet. It is a pretty constant mixture. There can be some slight variations, but the air that makes up our atmosphere is a pretty constant mixture of gases. And it serves two main purposes. One, it's a blanket, and two, it's a shield. It keeps in the good stuff and it keeps out the bad stuff. And Earth is not the only planet with an atmosphere. Within our solar system, Mercury is the only planet that doesn't have an atmosphere. The thickness and composition of atmospheres on different planets can vary, but most planets have some layer of gas that surrounds the planet. So, air. Air is the name for, we use it generally, but it is the scientific term for the precise mixture of gases that make up our atmosphere. It is mostly nitrogen. Nitrogen makes up about 78% of our atmosphere. Oxygen is second at 20.9, or we'll say 21%. Then most of what's left, 78 plus 21 is 99. Most of what's left is going to be argon, and then trace amounts of other gases. We are right now at about 0.04% carbon dioxide, so even this graphic is a little outdated. And there's small amounts of other things, but about 80% nitrogen, about 20% oxygen, about 1% argon, and then small amounts of other things. That can include neon, a little bit of helium, krypton, methane. All of those are in very small amounts in our atmosphere. There can also be a couple other components that fluctuate more frequently. The amount of water vapor in the atmosphere can change daily. Dust particles or any solid ash, things like that, that can be suspended in the air. And ozone, which has the chemical formula O3, which both forms naturally and can form from pollution, which I'll get to in just a second. Some of these gases are changing. Like I said, that graphic was out of date. Carbon dioxide is on the rise. It is at 0.04% right now, or 400 parts per million. But carbon dioxide in the atmosphere has been increasing since the dawn of industry, and we can track that change over time. So it's been about 50 years since we were at 300 parts per million, or 0.03%, and we are now up closer to 0.04%. Ozone, I said, can fluctuate and it can form naturally or from pollution. Ozone is O3, or three oxygen molecules all bonded together. And it forms naturally when ultraviolet rays break apart O2, and then a third one gets added in. Chlorine will come in there and make a mess. But it's important because it absorbs ultraviolet rays from the sun. It protects us. Sunburns and skin cancer would be much worse if we didn't have ozone. It could cause mutation and cancer. So having ozone is really important to protect us from those ultraviolet rays. Ozone is actually toxic to breathe, though. So if it was at lower levels, if it was closer to Earth than it is, or where we stand and walk, it would not be very good. Luckily for us, ozone, as it exists, protecting us, is higher in the atmosphere. It doesn't, however, last forever. If there are contaminants in the air, you can destroy ozone molecules. CFCs, or chlorofluorocarbons, rapidly break down ozone, or O3, in the stratosphere. So it's been a while now, but a couple of years ago, there was a hole in the ozone layer because we were using too many CFCs. It broke down. There was a massive gap, a hole in the ozone layer that has, now that we have cut back on CFC usage, kind of healed itself and closed back up. But making sure that we don't end up with ozone holes in the future is going to be incredibly important. So ozone naturally exists, and where we would like it to be is in the stratosphere. That is where it is helpful to us. But if it were down low, if it were at ground level, it could cause a lot of health problems. And ozone is actually one of the biggest contributors to air pollution. When you look at a smoggy city or pictures of places that are really polluted, a lot of that is ozone, which you wouldn't think of as something dangerous because we know that ozone protects us from the sun. But at those low levels or close to the earth, it is very dangerous. And a lot of that pollution comes from cars. So I've hinted at the layers of the atmosphere. I've mentioned some of them. Hopefully, again, these are familiar, but we'll talk about each of the layers in depth now. As you move up through the atmosphere, which is how we're going to go through this, we'll start at ground level and move into space. The air becomes less dense. Above 100 kilometers, which is in the thermosphere, there's essentially no atmosphere. There's not a lot of air left. There is atmosphere, there are gas particles, but they are so spread out that it's not really what we would consider to be a breathable layer. There's just not a whole lot of gas. It is so spread out. 50% of all air is found below 6 kilometers, and 90% of all air is found below 20 kilometers. So as you go up, the density is going to change rapidly. Here's another graph that shows kind of different things you can expect to see. So weather happens down low. Airplanes still are fairly low. Remember, 90% of all air is under 20 kilometers. So most stuff happens under 20 kilometers. You can see the ozone is kind of around 20 to 40 kilometers. Polar lights, or the aurora borealis, and meteors tend to blow up much higher, near where there are spacecraft and satellites. So let's go through layer by layer. We live in the troposphere. This is the first couple of miles, up to 6 miles above the North or South Pole, 10 miles tall at the equator. Temperatures are what we're used to. This is where most of the mass of the atmosphere is. Temperatures are what we're kind of used to seeing with weather. This is where weather occurs. This is where the clouds are. This is where we live. So the troposphere is kind of the big one in terms of activity. The line where the troposphere ends is called the tropopause, and then you move into the stratosphere. This is 6 to 10 miles thick. This is where the ozone layer is. It is dry and less dense. Remember, as we go up, the air is going to get less and less dense. And the temperature drops in this layer. So you might have some high flying planes, weather balloons in the stratosphere, and this is where you have the ozone layer. Stratosphere Tower is the name of a building in Las Vegas. It does not actually reach the stratosphere. No building is tall enough to reach the stratosphere. After the stratosphere, you hit the stratopause, which is the line in between the stratosphere and the next layer, the mesosphere. This is 53 miles thick, and temperatures fall to negative 93 degrees Celsius. Remember, 0 degrees Celsius is where water freezes. So this is really cold. The layer here gets excited from ultraviolet rays. This is where this energy from the sun is interacting with gas particles. So this is where you will see things called sprites, which is excited atoms releasing light. And this is where most meteors tend to blow up in the atmosphere. The end of the mesosphere is named the mesopause, and that begins the thermosphere, which goes to 350 miles high. It is sometimes called the ionosphere, and this is where a lot of energetic photons from the sun are being absorbed. This is actually a really hot layer in the atmosphere, but I want to make something clear here. Temperature in physics and in astronomy is defined by how much energy the particles have and how quickly are they moving. Up in the thermosphere, and you think about being in space as cold, the particles, the elements that are up in the thermosphere are very excited. They are moving around a lot rapidly as they absorb this energy from the sun. But they are so far spread out from each other that all of that movement we wouldn't really register. This, if you were to go outside, if you were going on a spacewalk in the International Space Station, it would feel cold because the particles, the gas particles, are so far spread out from each other that even though they have enough energy to be considered really hot or really high temperature, they are never running into each other and they are never passing that energy along. So the temperature of those particles can be 1,000 degrees Fahrenheit, but it is still, space is cold because those particles are so far spread out from each other. And the final layer that some people don't even classify as a layer is the exosphere. It's hard to kind of say exactly where the atmosphere ends because it just gets more and more spread out until eventually we decide it's too far spread out to be considered the atmosphere anymore. So the exosphere is where things are being so far spread out, maybe the gas particles aren't being pulled to Earth as much, and so they are escaping into space, that the atmosphere kind of slowly fades away. Not everyone will consider the exosphere to be part of the atmosphere. This is where our satellites orbit, so it is pretty far off from Earth. Here it extends to 10,000 kilometers because here it's just the gas is slowly fading away, and we can't really draw an exact line and say this is where all of the gas ends. But those are the layers of the atmosphere.